Oh wow, I'm online. That is quite amazing. Let me just see whether I can be visible too. Oh, this is very good. I just switched streaming software. The other stuff really was not. I was not having any joy with that at all. So OBX is working much better. I like this software. I don't know why I ever went to the other one. So where have we got to? Some progress in some strange geometric way. Not much algebra. Some algebra actually. Well, stuff for the algebraicists, not for me. That's not my skill. I'm a geometer, and I don't often understand the very difficult proofs involved in some of this stuff, but sometimes I can see the overall picture. And then I come from a field of being a programmer, so I've had to, if I'm given a spec where someone says, all right, you've got to get this thing out of an impossible system where you can't like do this and you can't do that and you're allowed to do this, and then you've got to go over to this system, like cross the 32-bit to 64 to back, and neither can talk to the other. That's got a word, and that's called a thunk. And thunks are horrifically difficult to write in code. They really are a problem. They don't really fit. In fact, their algebra is what we're trying to describe, because these things don't act like functions. They act as what is called coroutines. So it's quite hard. You see, that's one of the problems that we've got with trying to describe physics with mathematics, because we like to, physicists like to describe things in terms of actions, and mathematicians like to describe things in terms of functions, and funny enough, computer programmers like to design things in terms of functions too, because actions, although they're really important, their algebra is quite complicated, and is not something that's really been, that's basically what we're trying to explore, is the algebra of coroutines. And they behave a bit like functions, but they're not functions. They're like a square root of a function is a good way to describe what a coroutine is. So a function is like a coroutine squared. And that should immediately ring bells for gauge theorists, because they say gravity is the square of gauge theory. And I see it the other way, actually. I see it that gauge theory is the square root of gravity. And that's the fundamental thing that we're dealing with here, is gravity and how everything else emerges from it, and how to discretize gravity. Now, and obviously this isn't going to be an easy problem, but the thunk is the thunk is an absolutely critical tool for crossing event horizons, and I'll explain a practical technique for doing it. This is not just this is not there's this easy way of crossing a black hole horizon. No, there's some practical code here, and it is horribly complicated. I mean, I was just looking at it, I wrote it, and I was having to read my own comments on it. Thank God I did write comments on it, because it's really horrible. And what it is it's kind of like a way to represent. Now the problem is, you can write a coroutine pretty easily, and like languages try to write coroutines. They try to add coroutines generally on top of a language, but that doesn't work. They're all horrible. Coroutines have set a major problem for computer scientists, just the same way that gravity sets a major problem for particle physicists. And they've basically got the same, you have to use the same techniques for both. But fortunately, because I come from that kind of, I went into maths, and I don't know why I went into programming, but actually I only found this solution from programming in 2021, and I don't think if I'd actually had to face this problem as a technical problem of actually having to cross these black hole boundaries and tunnel back information from another system where the physical rules are different, that I'd recognise that this was exactly the same situation, and then seeing that basically the techniques that I have escape from categories, because you're in one category and you're trying to escape and get a result from a category higher. Or but that's normally the situation that you're in. Say you're in a 32-bit operating system and you're trying to get a result from the 64-bit system. You're living in different universes, so you have to somehow do something to get that information there and back. And it's not just a case of a physicist or a mathematician thinking, oh gosh, I've got to like think of some smart way of doing this. No, if you're a computer programmer, you don't get your job done if you don't do it. So maybe that's why I landed up doing computer programming for as long as I did, and also to understand what it means to write a functional compiler, which is an extremely difficult job. So it's like you continually need to be reminding yourself of what you're trying to do. And so that, if anything, is my major skill, is denotational semantics. If there's anything that, even this geometry stuff, I'm very, very visual, and I have to like see things visually. And like some people, there's that shut up and compute stuff with quantum mechanics. The problem is I couldn't start. And when I started looking at quantum mechanics, all that popped up, I have a loop amplitude to start with. It's like, don't forget trees, and no trees yet. We've got loops at the beginning, and that's it. We've got to kind of, that's why we've got this theory of loops, and we're trying to square root it. And now the square root is obviously you've got a Riemann surface there, two-sheet Riemann surface, which is giving you immediately, you've got double covers everywhere. And what on earth is going on with SU3? Now, I've scribbled down a few things because there's so many things I'd like to talk about here, because really all this information has been coming to me far too fast. And so I've got to kind of scribble it down as it comes to me, from whatever dimension it's coming from. But basically, I'm writing down a whole load of stuff that's known here. There's some stuff that I'm adding to here, a few little tweaks. But you see, that's the thing, that's what I'm trying to say. We're working within a framework. This is exactly what you've got with a computer programmer. You're going to be given a spec. So what the spec is, after huge amounts of amazingly intricate work, which I couldn't replicate, and someone like John Donahue can. He's an expert in this stuff. Yeah, amazing. I've watched him go through this, and then I watch it again, and then I watch it again and again and again and again. And what I picked out of it was really that his sixth talk, if you can get through to it, if you can work through all the amazement that it takes to get there, it's like got a revelation at the end, which is that gravity as a scattering is not universal. It's only the gravitational potential that's universal. And so what I've done here, just to make things a little bit, just change it just a little bit from what John's doing, is instead of writing it in terms of potential, I've just taken it, I've just multiplied it all by an R just to make things really explicit that we're now kind of dealing with a force, not just a potential. So what's the potential force that's acting on this? Okay, I know it's a Newtonian view, but we're not dealing in a relativistic framework, remember. We've actually got Euclidean clocks here. So we're kind of looking at the outside from this system as though we've got an absolute frame of reference, and we'll find that that's very, very important, because we'll want to synchronize every clock that we've got in the system. And this is like a computer programmers. This is a spec. We're given a fixed number of dimensions, 11, and what can you do? How can you make a reality out of that bundle? And I know I'm not using bundle in the fiber bundle technical sense. I'm talking about API sense of just wrapping up everything, sticking it behind an API firewall of some type, so that you can't get in, you don't know what it is inside it, but it's like a Turing oracle that you can put answers in and you can get answers out. And that's all you can do. And then you can kind of make that, and that basic option is you see that thing of putting answers in and getting answers out, that's not a function. that's a coroutine. And so this is where basically we're thinking in terms of functions to solve this kind of problem is not useful. What you need is a bunch of equivalences in category theory to actually show that you can start to replace functional calls with jumps. And so this is basically the technique that's called tail recursion, where if you think about it, if you there's so many. Look, I could be talking for so many hours, and Wiki exists, so it's easy to check up on all of this stuff like tail recursion. But let's look at this formula. It's a correction to Newton's gravitational force. You know, it's like Newton wasn't so far wrong. We've got now. What does this r squared mean? This r squared means that we've got something expanding on it's a sphere, a two-dimensional surface, a two-dimensional sphere. And so that's the first approximation. Then we get the correction to the gravitational force from Einstein. And that's this strange 3g over r. So we're getting a four-dimensional. So this is talking about an m plus n. Very important, this m plus n. So if m equals minus n, this cancels out. So if we've got negative mass stuff, which we definitely do have a lot of that stuff hanging around, then this term actually cancels. So quite nicely, we land up with the coupling between the positive and negative modes as actually being just this quantum term. It's independent of the mass. It's just dependent on there being an interaction of some type. Look, it's completely mass independent. So, and this is where, all right, so we're going, let's count up dimensions. 3, that's for Newtonian gravity. If you don't have 3 dimensions, you can't have planets and spinning things and orbits. 4, we need a clock, and okay, it's a bit more warped up and mixed up with this, but then, and that's our clock, if you like. That's our local clock, and then there's this other one here that's hanging around, and that's our quantum clock to kind of like tick things forward independent of their mass. So we've got to just have something that just factors out all the mass together. And then after that, we've just got a bunch of high frequency and low frequency noise. And now the fact is that using UV equals IR, we can basically forget about most of this stuff. Yeah, there's a bunch of theories that will, there's a lot of research not done by me at the moment into all the theories that would give this effective field equation, and there are quite a few. So, but basically, this is what is known to be likely to be true, at least partially true at one level. About there might be well, we know there are corrections, but we're not exactly sure what form they'll take, and they will probably be, in a certain sense. Well, no, I've actually started looking into it, but the algebra is just way beyond me, and is more up someone like Ed Witten's street than me. It's just like, yeah, he's the kind of guy for that stuff. It's a Noel Baker, Ed Witten kind of algebraicist, but with a huge amount of geometric function theory. And so that's really where things have to collide with geometric function theory and Berling and all of that lot. So, and the quasi-conformal lot, because that's how you flatten out these maps, and I'll explain how you do it. All right, so before we start talking about all of this stuff, let's just run down this stuff here. So M theory, 11 dimensions, all right, and let's just think about this logically. So we got one clock there, that's what we did. We got a compact clock, all the dimensions are compact. So we're just dealing with basically an 11-dimensional toroidal space. But it's going to have some weird, complex, extremely complex structure, and we know that we've already found that in 2 dimensions, and that will have a dual as well, as I'll explain. Because I used to have a comment here saying that there are a bunch of no-go theorems that basically force you to do this kind of thing. Because there's like a theorem that you can't do a chiral gauge theory on a lattice. So what do? Well, we have another dual lattice that we do it on, basically. So we have 2 lattices. This is position, this is momentum. And then we have our thunks that go between backwards and forwards. Now, how do you write these buggers? It turns out that there is a way. Yeah, it's this algebra, but this is basically the algebra that we're describing, and I'll give you the starting formula, the generator for the algebra. And it's actually not too hard once you've got your head around. I've got the full algebra actually written out and tested somewhere. It is considerably harder, but it takes, I don't know, a few pages more than just the generator. And you can, what I'm saying is you can abstract all of that weird machinery that is there. You can make it covariant, because it's not, if you look at the code, the basic version of the code I gave you, I'll give you, it's not covariant, but somewhere I'll try and track down the covariant version of it. And that's where basically I found this structure, and it's just a universal structure that kind of jumps between it can convert a functional a series of recursive functional calls into a series of coroutine jumps, and then but you've always got to do the unwind process at some time, and so what it allows you to do is just basically forget about the unwind process, because you can be doing operation. Okay, forget about it, and then it could go, all right, I've got to, like a much better version of exceptions, which are basically trying to do the same thing, but they don't work because they haven't worked out. The exceptions don't work because it's all the same algebra with coroutines, and it's all got to be thought out consistently. And this is where denotational semantics comes in, and the only way you can do it properly is by cutting down the number of increasing the constraints on the system. So lifting out lifting out every degree of freedom you can possibly find, and sticking it into a boundary condition. So you're just making a minimal theory that's got as few internal degrees of freedom as you can, and just pulling them all out to the boundary, everything. And if you think you can't pull a condition out, think again, because you normally can. And it's just a puzzle as to how to do it. And actually, this whole weak observation, self-observation, automorphic form, generating a weak reality out of the no-born rule, but making consistent weak reality. So we're actually like making observations of the multiverse and projecting them out. So we're making a kind of flash observation of the entire multiverse, and then each thread of the multiverse can run independently of each other. So we basically have to make sure that they all have no or little gravitational influence. There's possibly going to be some way. There's always a way round. The universe can always be bigger. So we're never going to find out all the answers, but this kind of top-down approach can certainly fix some problems. And now, okay, this is where I really wanted to start, because I probably lost all the notes from things about what I was going to say, but I was going to talk about Noel Baker. And Noel, I've gone on about Noel Baker because, he was incredible, and I hadn't met anyone like that. There was one time where I just started first year PhD, and Noel said, "Oh, you got a paper for me?" I said, "Yeah. I've been working on this." And so I was reading through it. It was like, I read through page 1, page 2, page 3, page 4, page 5, page 6, page 7. Noel is like that, and I look back at him, and he says, Jonathan, on page 1, you say, and then I just go, I can't even remember what it was. It quickly went to the bin. But I think it took me about 18 months before I could get a paper past Noel. And one thing that rubbed off on me is that whenever I pick up a maths book, I look at page 1 and I find the mistake on it. And it's pretty well every book. And because every book makes some starting assumption and it's probably wrong. So we have to start with like no assumptions of anything. That's why every time we make an assumption, we then got to remove it and see what we can do without it. So that's my philosophy here. It's just keep going down and down and down. But what have we got from this? We've actually got some kind of structure now where we can take our 11-dimensional theory, take this one clock, okay, and you can see it all matches up nicely here. So we get one clock, 2 lots of 5D. 5D, well, we got to split those into 2 lots of 4D plus 1 clock, because every time you do one of these Riemann surface splits at a singularity, you've got to add another clock, otherwise you can't do anything unless you've got a sense of time. And so then we go down again, but you can't have planets in this space here. It's different. And then, but down here, blang, this space splits again. We can have particles in all these spaces, and we'll see what they are. And then 4D, you've got 2 lots of 3D plus 1 clock. So a lot of these extra dimensions here, when we're constructing a space out of this 11-dimensional M theory, are just basically clocks. They're not much more than that, and they're just curled up in a ball. And because we're not trying to do all of that Calabi-Yau stuff, you know, we're not trying to get them propagating on a 10D space. We're trying to get them resonating between 2 5D spaces. And the idea is those vibrations are carrying entanglement. So a 1D vibration is carrying a point-to-point entanglement, and a 2D surface is carrying a 2D to 2D entanglement, but can only do that in a conformal manner. We'll look at that. So when it joins to another domain, it has to join on a circle, bang, because you have to stop all the vibrations, and those vibrations are the modes, are the superpositional modes. So every time we meet on a thunk, we have to stop time. Sorry, I'm calling them the thunk event horizons, and it's the same thing. The technique is always the same. When you're transitioning between, imagine we've got 2 laws, we've got 2 regions, a left-handed region and a right-handed region, and we've got physical laws in this side, and then we've got physical laws in this side, and we want to switch chirality. Yeah, well then what we've got to do is that any particle that is on the joining point of that, we have to stop time for that particle, and they go, okay, turn it around, or we'll send some of it, but we're actually going to have to like leave a little shell of it, I like to think about it like a walnut being, so you've got your photon coming in like that, and then it goes click and splits into 2 parts on the event horizon, yeah, showing its guts. And so and then we get these opposite dimples on the event horizon, so one bit is pointing up and one bit is kind of pointing down. But then the thing is actually the way I'm doing it with my hands is not exactly right, because the event horizon is actually flat. Yeah, it's geometrically flat, even though it looks curved to us. That's not. It is actually geometrically flat, and that's essentially what loop quantum gravity tells us before it then goes on to try and tell us it isn't. So I'm treating loop quantum gravity as a no-go theorem for dodgy loose tetrahedra with wiggly ends. You've got to lock them down, and you've got to stop time. And other than that, you're going to have problems. That's about the only place. And so what that's telling us essentially is the only place that quantum gravity really works is event horizons, because that's going to give us a nice correspondence that we can work with. Because fundamentally the equations are so hard, unless, but we know there's a number theory correspondence. So the thing is these are not measurable functions that we're dealing with, they're analytic. And so that does put them into a slightly nicer class, and where you can, at least if you're an algebraicist, do something with them, which you can't do. You see, I come from the transcendental situation for school, and we most often don't have to deal with those things because they're just the equivalents that we get in the transcendental analysis simply are not manageable in any way, so we don't deal with those structures. We just have to deal with qualitative stuff. So that's what I'm trying to suck out of this very difficult algebraic problem that has got, well, as twisted as any transcendental problem. It is involving the same techniques. And it needs a whole book thrown at it. So where are we now? Okay, so we've looked at the effective field theory. So this is just, I mean, what an equation, the amount of work that went into that. I think if anyone really wants to be serious about studying this stuff, you have to get into this, and it is painful, but I'd love to see how to get to this equation from this, and I don't know whether I'm capable of doing that, because that's not my area of expertise, as mentioned before. But what I can say is that it seems to have got a long way by assuming the no-Born rule, and instead using the automorphic Heck operators. Automorphic weak observation. So this is a notion that, you see, when we were looking at the Aharonov situation, we always had the problems of how to equate near and far field. And once I saw this, I thought, well, again, that's a problem for other people, but I can see it can be done. And I can see how it can be done, and I can see how it fits with Langlands. Langlands is basically giving the existence proof for this kind of stuff. And that's where I came in with the question that Langlands has the answer for, and that's why this is so incredible. And it was like it just popped up on my YouTube feed, Langlands talk, and it was like I was absolutely transfixed, because he seemed to be thinking about it in a very similar manner to the way that I did. It completely surprised me. And because I come to this from like thinking, what on earth is going on here, and how can we do anything about this? Where to start? But okay, we've got, it's like we have this extremal solution where we've got these Yang-Mills equations, but they're not supersymmetric yet. So we need to make them supersymmetric because of the lattice no-go theorem. So the lattice no-go theorem is telling us that we can't do a chiral gauge theory. So we need these thunks between a dual lattice. And now we know we have some information here. We have a lot of information, actually, about what is actually going on in this thunking process, in the particular dynamical situation that we're doing. What we're doing is essentially an FFT without disturbing the opposite variable. So if you've got the thing is we're trying to save on stuff. We're trying to store our momentum and our position using the same bits. So instead of just using, it's just much more efficient to do that because you're halving the number of bits that you need. But you're also setting yourself this major problem on how to get objective calculations out of it, because you can compute position here and compute momentum here. And so the thing is we're really going to want kind of combinations of those things. So all that we can really get thunk-wise is maybe setting up a thunk from there to there, say, and then a thunk back, and then maybe loops that loop around and iterate for a bit, and then land up one side or the other, and then eventually all unwind into some great big time-like loop. And now this is where Gödel is. This is a kind of extreme version of Gödel's universe. Gödel's universe was a spinning universe, but in this universe, this type of cosmology, every point is in a closed time-like loop. That's what we're trying to generate, and it's that each one of these things forms essentially an algebraic surface with an objective geometry on it. Yes, we're never going to be able to calculate what that is, although we can actually take some very good guesses about what the initial data is, because of the way that the numbers are going to be stored in terms of continued fractions, because we're not going to be wanting, if we're going to be doing any real arithmetic, we certainly don't want to be doing in even, there might be some stuff that we want to do in binary, but most of it will be done using Mobius transforms, because we can actually do those accurately, and we don't need to know what those real numbers are. We can just be dealing with the modular group, so we're just looking at the numbers as, and that will give a wonderful type of non-locality to the space as well, and you get great big voids and things like that from continued fractions where the continued fraction map is not ergodic, and that was the kind of stuff that Noel and me were looking at. And there's a bit of a school in there's the Hurwitz school in the one that we did, and the Hurwitz school gives you is another way of completing to give you the real numbers, but it's just much more modularly invariant. And the one that we did that was there's a spin half and mine was spin 1 basically, and it's a spin 1 ones that have huge voids. In fact, the matter only exists in the set of measure 0, which was what Noel managed to prove by using transcendental bounded distortion methods. Oh, what a beautiful proof. I mean, oh my God. And then there's still a kind of open problem. I consider it solved because I'm a geometer and I can see why it's true. But for an algebraicist, oh, good luck. It's horrible for an algebraicist. I don't know what I would do. I tried doing a bit of algebra, but I'll tell you about that at some time, maybe not today. But if anyone's interested, tell me. And right, so we've got this extremal grid, which seems to support this Yang-Mills. Now this is immediately telling something really amazing, that this is not a square grid. It's like, I don't know what the exact dilations of it are, but they're actually extraordinarily important, because you can see that you've got these subtle ratios going on between the ellipticity of the thing that means that you've got a long side and a short side, and so these sides are going to have different communications. But because remember, what we're doing is we're just trying to treat this in Euclidean space, and just to get around the Aronoff problem about the near field to far field, what we're going to do is put the thing in thermal equilibrium by basically treating this on the torus, yeah, and then we treat each of them as a Schrödinger emitter with no, and itself as being its annihilator. So So it goes create, annihilate, create, annihilate. So this is a permanent phoenix like circuit wandering around in here. And then we're going to get the dual over here. So this is our position space and this is our momentum space. And but the thing is you can already see that we've got some dilations in here. And in fact, if you think about it, what the gravitational field is doing is just doing this on a microscopic scale. So we're getting like all these microscopic kind of ellipsoids that are all just jiggling, not jiggling and jostling, but they're all pointing in different directions. And that has a solution. There's, when you've got that situation, and we've actually got that with an analytic situation. It's again easier than the situation I'm used to dealing with, where it's that measurable. And so that again, that's really important. That's what, because I would always deal with it when it was that I would deal with the measurable version of this. I didn't really even know that there was an analytic version of it, and I looked at the analytic version of it and I thought, Ed Witton. And so this, what we have is we have this measurable medium map to flatten it out. So this is basically what us geometers do to take these horrible elliptical fields, gravitational ellipticals that got heat, it's like noise, and just flatten out the whole thing. And if you look at the theory, it's all about isothermal mapping. So it's all about thermodynamics, this thing. So this thing is behaving like heat on here. And we're just essentially cooling it all down, right down to absolute zero. We're taking away all the noise. Sorry, I can just see I've done that. So we're taking away all the noise and we're just flattening it out. And now we've got a nice local chart. So if there are no interactions going on in there, we can treat it like it's the bulk. So this is basically what the whole idea is, to get from the very complicated Einsteinian metrics and actually flatten it out on the world sheet. So we can, again, page 1, if you look at the Green-Schwarz-Wittenberg, page 1 is the Nambu-Goto action, and that's the mistake, is the square root of the metric. As soon as I saw that, it was like, and so this is just basically, we're just always dealing with squares and square roots and the associated Riemann surface and how to, and so basically what we're doing by this is it's exactly that technique before, where we've taken the metric, we've actually just replaced it with all of these kind of heat terms, these multicolored grains of rice, and then just turned them all into nice spheres of multicolored spheres. And those spheres are limited in their colors because I haven't written it here. But considering, this is exactly the line that 't Hooft and myself were thinking about. If you're discretizing this system, there's one field that stands out. Well, there are a few fields that stand out, but there's one that just is like a smoking gun. And that's GF27, the Galois field 27. It is just a thing of beauty. And now the reason it's so important is because, as well as being that, it blurs the difference between a state and an operator. Because it's a Galois field, that means we can be representing each of the pure states in our quantum algebra as an operator as well. So this is another duality. I did have this written on the board, but it's actually really important, the fact that GF27 has this essentially it can play multiple roles depending on what you want it to do. And the other thing about GF27 that makes it so neat is it looks like you're just trying to represent SU2, but it turns out that it's got a representation of GF8 in it as well, so it can represent the electroweak. So basically it's a single field that allows us to represent all of the standard model interactions, including, I guess, the supersymmetric ones, but I haven't checked that yet. So I think that's that little bit done. I've done the M theory clocks. Oh yeah, count the clocks, 3 generations. So take the electron here is less massive than the 5D tau is more mass, and then even more massive is the muon and then the tau. So we can see if each particle we're going to get 3 generations of it because of this. So what those 3 generations are telling you is how deep the dimension stack we are existing. So and then you can go down one step more, which is 2D plus 1 clock, and so those are our clocks. So we still need the universe can have a sense of time, but we need a sense of time, and then it's like stop. So you can see we can't really, and the other thing is that what I didn't write here is that this is absolutely key in YM theory and no more is the first strings theory revolution, where basically it would show that string theory, well, not M theory, but the basic string theory only worked in, superstring theory only worked in 10 dimensions, because otherwise you wouldn't, the weak force wouldn't work. So basically it's just forced. Everything is forced. And then if you think, all right, if you're thinking like the Great Spirit would, well, you want to be able to do every type of string theory, given that it's a theory that is good. You might even want to be able to do stuff in the swampland. It's like, why restrict yourself? What you want to be able to do is say, how can I extract the maximum amount of physical functionality from the systems that are given? And so some of these bizarre swampland, well, first of all, we have cut out, look, most of the swampland consists of absolutely nonsense manifolds, because we've essentially reduced it right down by taking a lot of the clocks, and we've got a bunch of space-time dimensions. So all we really need to check is that this thing is Ricci flat. So we need to check that it's generating some kind of Calabi-Yau manifold, because otherwise we won't have the correct constraints that string theory requires. So again, that's not my speciality. Someone else is probably just like an expert at that. So, which allows me to move on quickly. And I do other things, you see, so I haven't got 6 months to write a paper on this. The other thing is, all right, this equation, so like this is where it just makes absolute full contact with Langlands, because you see, this is the equation I wanted to solve, and this is the equation that Langlands was saying, why do we land up with uniqueness for a question that's like doesn't seem to have any bearing on anything? And it's like, well, yeah, we need uniqueness. We really want to be pinning down theories, and we really, and so what is this equation saying? Something is saying that something's not an eigenvector. And so what I've done is I've put it into a form that makes sense here. Oh, by the way, down here, and I've missed out a little bit, this is the basic formula here, and the idea is that we're putting the Higgs scalar to create that mu term. And if you try and do it and you put like e to the I phi naught, you'll find you get a mu that goes bigger than 1, and we're not allowed that. Yeah, so we've got to do another thing to map it to be less than 1. So we've got an absolute kind of bound on the amount of, well, we can't ever squish it more down to a line, but you really want to keep this number down to a number that's less than k, you see. So there's a bit of mapping to get from this phi naught to the mu, and it's quite intriguing, and it seems to require a double cover itself. So I've just written mu here for the moment. I'm sorry, I did have another version where I'd written a little bit more about it. And the other thing is that this is the positive form of the energy-time relationship, and this was actually the work that this is the thing that I proved that I sent to Noel, and he said, oh my gosh, I think he got it. And you see, the thing is this is basically the same thing. So this is telling us how much we can break the energy requirements and the constraints in order to store extra additional modes on our strings to store superpositional states. But really, if we're doing geometry, what we're trying to do is pull everything down to its ground state. But we have to be aware that we're doing that because it's going to disturb things. And it is going to take a tremendous effort to solve these algebraic equations. I mean, they are so intricate and beautiful. But so we actually seem to be getting somewhere, but we haven't got to the stage where we can collapse it, obviously. I mean, look at this pattern. What it's doing, I don't quite know, because we've got, you know, identification. So where I was drawing these near field, far field diagrams, we've actually got these identifications going on. And remember, we're trying to model every interaction like this so that no interaction, once we do this, every interaction essentially becomes independent of every other interaction. So as long as we make the thing in thermal balance originally, then we can ensure it's going to stay pretty close to thermal balance all the time, apart from peculiar events that can sometimes happen and unhappen. But so right, I think we're doing pretty well. I didn't expect this was going to go so quickly, actually. Why don't I leave, because it's been such a hard slog, I'll leave the actual source code till next time, and we can start to look at how to implement these thunks even in strongly typed systems. And that's what the trick is we really want to get a kind of generic way of dealing with coroutines in a functional way. And so then we can actually start to get some kind of method of finding out how we can be cycling information forwards and backwards. Now, what I was going to say is oh gosh, all the time I've been spiraling around the most important things here. The corrections to the Feynman diagrams for the standard model and all the related models, all the Feynman diagrams. All right, now I won't draw the normal one because that's everywhere, but we've got a photon coming along like this. Actually, it's probably better to actually not think about a photon. It's probably, no, a photon was pretty good. I've drawn it actually. That's absolutely right. But the Higgs will be interesting too. So it decays here at this singularity, and then we get our electron going off on here. And I've marked that E minus there, but then I've put it supersymmetry, which is behaving, you know, which is this is the whole principle of lifting out degrees of freedom, because it's a quantum number. Anything that is a discrete value has to be lifted out to be a quantum number. So this is the whole Einstein gravity approach, you know, quantum numbers function n to n. So cut out all the, we really, that's what the real, taken to its extreme, we want to thunk our quantum mechanics from n to n. And then when we've done that, then we Gödelize it. And then we can inject a particle with its own Gödel number, and then it can reference its own Gödel number in its own interactions, and then that's when you actually get a powerful system as a programmer. because then you can make the thing fully alive. You're breathing existence and soul into the system. Because then the things can start to behave, because they know, the one thing is, can a particle determine which direction it's moving in time? It's something that I haven't quite worked out yet, but we'll try and get onto that in a second, because we've got to orientate ourselves first. Alright, so we have our electron going off this way, and then we have a split going off that way, which is a positron, but I put the minus on the supersymmetry, so this is a boson now. So this is what, a selectron. And so this is the actual split that's occurring. This is why we don't see many positrons, because they're all selectrons. And now I did draw a little thing here, which is, of course, these two things are actually entangled across the event horizon, because we're in two 5D spaces. That means that everything between those two 5D spaces is kind of entangled with a string. So when there's a split, they've still got this string between them here. And they got two strings, actually, because everything is a loop. That if we're going to cut a loop, we're not really thinking about gluing strings, we're thinking about cutting loops. Because we're starting with the loops and trying to get the strings out of it. So we have our loop here, but this is actually spanning, is the event horizon that the photon has made. And because these two things have to be separated by a thunk line, that's the point. So this is the basic correction, and then you just run through it. Now, I haven't gone through all the rotations, because one of the ideas is you're meant to be able to rotate these things and get the same probabilities. But again, this needs to be investigated. Nature isn't telling us what the options are. We've just got to look at them all and see what works in what way, and are any of them forced for whatever reason. And so basically now we can give a model of how the scalar Higgs actually decays into a universe and its anti-universe. So we have a Higgs here, and then I'm just doing a plus here. Notice that I've got a vector of quantum numbers here. I'm working in the kind of Gödelization now, where we just want it to this is a Gödel number and this is its negation. So these are kind of symbols for me. That's why I've cut out all the indexes, just to show that there's something actually more, because this is a universe. So okay, all right. So this fixed point equation, why do we want this? Because this is telling us how many. This n is telling us how many times we're going to be looping around with our thunks, because we want to be able to evaluate. It's going to evaluate after 2n loops round this circuit. So basically, what we can do with this n is tune the length of the lifetime of our particle. So the bigger the n, the longer this thing will cycle for, until finally it becomes just an eigenfunction, and bang, that's it, no more. And so what this system is it's like, imagine you're stuck on your own and you want to see whether you exist. You shout and you hear an echo. And so this is basically what's going on. It's like, is there anyone out there? Is there anyone out there? And you hear your own echo, and it's like, oh, maybe if I go, is there anyone out there? Is there anyone? Yes, there is. Yes, there is. Oh, it's me. Oh, it's me. So you can start to make up these conversations with different hats on, and then all these you can start to interact with yourself in different ways. And so this is the whole notion of unification, that there is no single particle. Well, it's one particle that keeps on putting on different hats. And so one moment it's space, and then it goes, whoo, well, now I'll be an electron. Okay, now I'll be a photon. And it's just kind of jumping around, being all these different things, interacting with itself. Oh, I'll be a space-time. Now I'll be that. And of course, it's got to kind of stop its previous state to be able to make some kind of coherent reality out of that. And so this is where this whole notion of stopping time on the thunk. So, all right, I kind of proved, all right, the benefit of us having this 0 on the top. We have no other way. If you think about it, the only thing we can possibly observe in this weak observation is one complex number. That's about the best that we're going to be able to get out of this. And then we're going to turn this one complex number into our Higgs field. So that means we zero the charge on the event horizon. So the event horizon has got no normal charge. It's just got, I think, a hypercharge and weak iso spin. So it's just like a really, really, that means there's some really odd stuff going on up here and up here with these things. So the different dimensions are treating the brains, the thunks in different ways. So I can't possibly decode that clockwork, but it is basically clockwork because it has to be from the fact that we're working with GF27 most of the time. Now, the other thing that this kind of does is this is quark confinement, isn't it? The quarks are in their own SU3 group, so they can't interact. They can only interact via a thunk. So if we were to draw or you can imagine that model that I showed you of the black hole. All right, so we've got here with this 0, so the charges are very restricted that we can put. This is basically, if you look at the standard model, this term has just absolutely destroyed this Higgs term. But now we're using it to derive mu here, so it is the key term. It's the only information that so once we've got this Higgs field, we've done it. Okay, so all we need to observe is the Higgs field, and that is basically just inner producting two waveforms together. But the problem is that we're inner producting a vector with its own v, and this is what stopped one of the recordings in its track, because this thing is not a wave function. Yeah, it's a v of f. So we can't really deal with it like it was a wave function because it's an operator. This v is an operator. So what this is meaning is this v is acting as a thunk. Anything that we're going to have to get there and back and across it, we can't just simply inner product with it. So that's why. So getting this, if we could just inner product with it, then this final would just be the inner product. But we're going to have to work much harder to get from there to there. And the price of that is, the rewards of doing that are amazing, because that is the no monopoles. Because if we have no charge, no electric charge on the boundary, then there can't possibly be any monopoles, because everything comes in pairs. So what that means, that's the picture of the photons splitting apart like that. And so what we get, and then this is the loop quantum gravity, that each one of these little bits has 1 Planck area each. And that means that everything needs to be paired. Okay, so the Planck mass, we've actually got to double it. Well, the Planck mass isn't quite, we've got to adjust all the pi's and everything. But once you get that, you need two unit areas to make anything. And so, yes, you can consider the event horizon to be pairs of monopoles. So, no monopoles is not quite fair. There's no monopoles in the bulk. But then, essentially, you could consider the event horizon to be made of pairs of monopoles. And these things are the genuine superconductors. So when we're looking at superconductivity, what we've done is we've actually made event horizons in the lab already. Actual event horizons that we can manipulate. So that's very, very exciting. The other thing is, which way are we looking? Oh, it's page 1 again. Old galaxies, redshifted. Come on. Look, the whole thing is this: we start here and we're looking towards a brain. Yeah, so we start from imagine that we can't do it in 2D really, but imagine we're on this 0D thing, and then the event horizon is this plane across us. So we're kind of moving away from it, but we're not. It's very hard to see which way you're looking. But whenever I do it, I see that I'm looking that way, and that what the CMB is not this bit. Well, it is an echo of it, but everything is echoing off it. But what we're really seeing is this brain. And so then the idea is that these so-called red galaxies are galaxies that regards to are much nearer to the brain than we are, and that's why they're old too. So these are old galaxies that are just about are getting redder and redder and redder as they are about to cross the event horizon into the frequency domain. And because that's the thing, what gravity is doing is think about it, it's like a rainbow. What does a prism do? It's a fast Fourier transform. And so essentially what we're doing with all of these, well, they're not multicolored grains, they're absolutely clear grains of rice, thinking about it, except if we go into the neutron and places like that where these things will have color. But in our universe, this sector, things are absolutely clear. And so it's just quite yeah. So what's happening is it's varying the speed of light, like glass does. The curvature, that's what the function of the curvature is. So the role of the curvature is to perform a fast Fourier transform, and that works both ways. So curvature is not there to mess things up, it's actually doing the calculations that are needed to do all this stuff. Is there anything else to cover? Not really. All of this stuff, the Beltrami equation is all covered. Higgs, yes, the Higgs connection, the desperately trying to get an inner product out of this thing that is an operator, the Aronoff compactification, no starting till we got a loop amplitude and a weak observation of the Higgs field. Well, a strong, we want to just derive it basically. And then of course we've got all the fun with the Gödelization, because we can be putting a lot of intelligence into these things and soul. I'm really excited about this line. All the dimensions are compact. This is the model of a 5D space. Everything seems to kind of like add up with what the state-of-the-art theory is at the moment. And this clock stuff, just it is derived from some stuff I saw on that most amazing international studies for quantum gravity. So yeah, which I really, really recommend that if anyone has an interest in this, that they just watch every single lecture on there, because it does seem like things are moving quite well at the moment. It's looking towards, if we can get this, there's no monopoles. The GF27 is really, really, I think that's all falling into place now, and you know, Tehuft should be able to do something with that, I would imagine. And so really I guess that's enough for now. I'm extremely tired, and I hope you have enjoyed this, and I hope that you can, if any, you know, join me or push this forward or something, because there's something here and it needs to be done. And the other thing is, so what we've done here, most importantly, we have the Maldacena map here. So this is the holographic map that we so need. And this works for both the positive and negative curvature. We know now that we don't get supersymmetric strings here, and I mean we don't get the supersector here, and we don't get our sector here. So it's this principle of complementarity, and using this line as being the thunk line, as being the line that you have to cross to pass between two separate realities. Oh, and I'll leave you with the little thought experiment, which was one of the things that really, really helped me understand this, which was the notion of a computer game where you're told that at a certain line, left will turn to right on your controls, and you're trying to get somewhere. Well, you're going to have to stop at the line. You can make various versions of it, but there's no way to get across that line unless you stop on it. And so that it does seem to be a common feature of all of these things, that time has to stop on the thunk line. And I guess that just about wraps it up. So thank you very much. If you've managed to get through all of this, well done. And if I find any obvious mistakes, I'll post them up, obviously. And if anyone finds anything completely wrong with it, more than welcome to point it out, because as I said, I make mistakes, but sometimes I can see stuff that maybe people who are very focused on small details can't. So I don't know, it's complementarity. We've got to each of us do what we're best at. So I appreciate your time, and thank you very much. And if I make any progress with any of this, I'll post again. Good night. Bye.